So this is the next topic. It's quite an interesting topic, I hope, but it has both descriptive and calculation parts, and it's about boundary layers. Now I have to apologize, this is quite unusual, but I don't actually have PowerPoint slides. I do actually just have it like this, so I hope you don't mind. I'm just going to scroll down through it. So let's make a start on boundary layers. And the first thing I would like to mention is to remind you what we said last year, is that the forces on an airfoil or a wing are due to two main distributions. The first one is the pressure distribution. The pressure distribution is always normal to the surface. So, as you guys can see, it's normal to the surface at every point of the wing or the airfoil. The second distribution is the shear stress distribution, okay? And it's always the combination of those two distributions that will give you lift and drag. Lift and drag will also cause a pitching moment, for example. But that's it, that's the origin. There is a pressure drag, well, there is a pressure distribution, and there is a shear stress distribution that give you lift and drag. One of them is normal, and one of them is tangential to the surface. So, just to say here that this skin friction is the result of viscosity. The air is viscous, it causes the skin friction distribution, or the shear stress distribution. The shear stress distribution itself will lead to something called the skin friction drag, which we will talk about. So a big part of this lecture is really calculating things like skin friction drag, skin friction coefficient. Okay, so that's quite important. Now, in terms of the viscosity effect itself. Now, we know that air is viscous everywhere, not just in the boundary layer, okay? But luckily for us, we only need to care about the effect of viscosity inside the boundary layer. Outside the boundary layer, we don't actually care about the effect of viscosity. So the air is viscous, but the effect of that doesn't have any effect on the aircraft as such. It's only inside the boundary layer. Okay, let me just give you, in terms of the concept of the boundary layer, now we all take it for granted, but it's actually, historically, it hasn't been straightforward. So I'm going to give you a quick run of kind of events in terms of the development of aerodynamics and the development of the boundary layer, and how the boundary layer was actually quite critical, the concept of it anyway, and how it was critical in developing the science of flight and science of aeronautics in general. So if you go back to Archimedes, so he did a lot of work on fluid statics, not fluid motion. And the great thing we know about Archimedes is Archimedes' principle, the buoyancy force, okay? We all know about that. Then Leonardo, one of the first people to observe flows in nature. So Leonardo da Vinci, one of the pioneers in observing nature and observing how the flow behave. And if you came across some famous pictures of his paintings, like trying to show us what turbulent flow looks like. So this was actually some of his work. And then Isaac Newton really started one of the first people to tackle the fluid motion in terms of mathematical description. So he went beyond that and looked actually the flow motion, not just the static. Okay, and as I said, trying to introduce mathematics into it. Then Daniel Bernoulli and Jean-Laurent d'Alembert, so they came after that, and they did also some work on fluid motion. We all know about the Bernoulli equation, for example, but also there was one guy, Euler there. Euler did a lot of work, but interestingly, okay, people were aware of the concept of viscosity. It's not they didn't know there is no viscosity. But Euler found out that it's actually easier to just ignore viscosity and develop some flow equations to describe the motion of fluid. And that led to what we call the Euler equations. So Euler equations are basically the equations of flow motion without viscosity. Of course, that's great, but that's not the full story. How about viscosity? So, two guys, one French guy, Louis Navier, he basically derived the full equations, including the effect of viscosity, to describe fluid motion independently. Someone in England George Stokes, he developed the same equations. That's why they call the Navier-Stokes. And they have viscosity in them, all right? So now, this is the first time there is a system of equations with viscosity effects included that describes the flow of motion. The problem is, even with that, scientists at the time, they were kept puzzled by some inconsistencies between the theory and the practice. They didn't kind of, and one thing I told you about in potential flow is D'Alembert paradox, for example, right? So that persisted for tens and tens of years. People really didn't understand why in real life there is drag, but the theory says there is no drag. And of course, that's because there are viscous effects in the boundary layer. And by that time, there is no concept of boundary layer. People have no idea what this boundary layer is. They knew there is viscosity, but they didn't understand it, in that sense. So for a while, there remains a lot of confusion. The whole thing was sorted in 1904 by Prandtl, because personally, I think Prandtl is one of the great physicists of all time, because he really solved the problem by saying, come on guys, we can't ignore the effects of viscosity, and the effect of viscosity is, he hypothesized that it is actually in a thin layer called the boundary layer, where the viscous effects are important. Outside of that, they're not important. And actually that led to a lot of work, a lot of development in terms of calculations or practical calculations of drag, because obviously drag is very important in aerospace. And if it wasn't for the boundary layer, we would have still probably not flown at the speed we're talking about now, because we don't understand what skin friction drag, and skin friction drag is very important. So practical calculations of drag, and therefore sizing of the engines, sizing of or design of the aircraft, all really came from finding out that, okay, there is this boundary layer where viscous effects are important. Not only that, even in terms of those people looking into heat transfer problems, okay, which become very important at high speed, for example, if it wasn't for the boundary layer, we would not understand what the heating effects are on the surface. So again, that shows how the discovery of a boundary layer, or the proposal for a boundary layer, was very, very important. So please remember Prandtl, a really great name. He's the one who described proposed the boundary layer. But there were actually people after him who came and extended his work, including Blasius, Schlichting, and von Karman. You probably come across some of those names in books, I'm sure. Right. So let's talk about boundary layer. Let me just skip over the time. We've got 6 minutes. So what is a boundary layer? A boundary layer is a very thin layer that forms around the body as a result of the flow around that surface or body. Okay. So it's a very thin layer. Thin in respect or in comparison to the size of the body. Okay. So for example, you have a wing of a span a few meters. The boundary layer on the size of a few millimeters. All right. So that's what we mean is a very thin layer. Now we know already. So for example here I've got a wing or an airfoil. There is a flow coming from left to right going through it. As it goes through it, this boundary layer forms naturally. So there is always that boundary layer, kind of small thin layer of air around the body. Okay, inside it, the viscous effects are very important. Outside it, we don't care about viscous effects. Now in terms of the speed, if you guys remember, we said exactly at the surface, the velocity is 0. That's called the no-slip condition. Okay, and outside it, the velocity, okay, or away from the surface, the velocity change. And it changes typically in this form. For example, if I'm a point on the surface here, this is like a blown picture. The blue layer here is what I'm trying to show as the boundary layer. And if you just zoom, if you imagine you're zooming the picture there, what you will see in terms of how the velocity changes from 0 at the surface, as you guys can see, and then it grows gradually through the boundary layer. So this blue region here is the boundary layer. So you guys can see it grows steadily until at some point at the edge of the boundary layer, the velocity is actually the same as the free stream velocity, and that's where we will define the edge of the boundary layer is. And of course, what is the source of this shear stress is the friction of the air itself inside the boundary layer. That's what causes the shear stress. What else I can say here? Now, there are two other situations where they're kind of the result of the boundary layer, or they relate to the boundary layer behavior. And one of them is, for example, stall on a high angle of attack airfoil or wing. We know as we increase the angle of attack beyond a certain point, the wing will stall. And basically what's happening in terms of the boundary layer is that the boundary layer physically detaches from the surface. It's no longer attached, or most of it is detached from the upper surface. And if that happens, you get this, what we call a separated wake. And the way to recognize it, if you look at the flow, try to visualize it, you'll find these eddies kind of moving in the opposite direction to the main flow, which is left to right in this case. So what causes this is the separation of the boundary layer. So in effect, that is actually a viscous consequence, this flow picture here. A similar picture is a flow around the flow cylinder. So it actually is easier to have a separated flow around a cylinder than an airfoil. This is what we call a blunt body. This is what we call a streamlined body. Okay. Either way, this is at high angles of attack, behaves exactly like a flow around the cylinder. And both of them, they're examples of the boundary layers separating. So we can consider them, as I said, as consequences of boundary layer effects or viscous dominated flows, as shown in the title. So yeah, high angle of attack, flow around an airfoil, and separation around a cylinder are both examples of boundary layer effects, i.e. the boundary layer separation. So how thin is a boundary layer? I told you already is usually on the order of millimeters. But let me just give you a picture here. This is an aerodynamic body. What do you guys think the speed here is? Yeah, most likely because of the shock wave, yeah? So it's actually a system of shock waves. We have one at the nose. You guys can see here, actually shock waves at the back as well. Anyway, we know this is high speed. So if you look very carefully, let me just probably zoom it out, zoom in, sorry. So this is the boundary layer here, and you guys can see it's quite thin compared to the size of the body, right? And this is what we expect in life. However, as I always tell you, is its effect is still quite significant on the body itself. So in the words of the great Prandtl himself, he said the boundary layer had marked results on the body itself in terms of the forces. So let me just summarize this before we go. So the effects of viscosity in the boundary layer, first of all, the energy, the kinetic energy is reduced because the fluid particles are rubbing against each other, because the flow is viscous and they rub against each other. They kind of take the kinetic energy from each other. So there is a reduction in kinetic energy inside the boundary layer. And this becomes more and more as we approach the surface. Also, there is an increase in temperature inside the boundary layer. That's another physical effect. That's probably just the same, heat transfer as well. So these are, I would say these are the main things. So yeah, reduction in kinetic energy, increase in temperature inside the boundary layer. So as I told you before, increase in temperature is very important for heating effects, which become very important at high speeds. Now, as I promised, I have to stop at 10:02.